skip down a little bit and talk about something that's kind of closer to what we've been working through lately. We look at this schedule. This is the number of weeks someone is sick in February, right? So I was either, you know, if I think about February, I can break it up into 4 weeks, right? It's 28 days long, so I've got 4 weeks. Was I sick in the first week? Was I sick in the second week, third, right? So the number of weeks I could have been sick during, well, 0. I could have been sick in 1 of those weeks, 2 of those weeks, 3 of those weeks, or all 4, right? Hopefully not the latter. But if I want an expected number of weeks or the mean number of sick weeks in February, how could I find that, right? Well, I don't want to simply use the general mean equation, which is add up these numbers and divide by the number of numbers I have. If I do that, I'm ignoring the fact that it's much more likely I'm not sick in any week than it is to be sick in all weeks, right? So I've got these different probabilities associated with seeing these different numbers of outcomes. Right? And that they're discrete, right? I have to be sick in 0, 1, 2, 3, or 4 weeks. So what I'm really looking at here, if I go to my formula sheet, right, minimize this for a second, scroll down here. Here I have grouped the 2 equations that you would kind of need to use for a mean or a discrete random variable. So first is the mean, and then I have the equation of the variance. Right? So we're looking for the mean or the expected value. So what it tells us to do is go through every single outcome, multiply that outcome by the value, multiply the value of that outcome by the probability we see that outcome occur, and then add them all up. Okay? So I go back to my example, right? I've got the mean of this discrete random variable. I pull up in the answer key, my bad. So what we're going to do is go through every outcome and multiply it by the probability that we see that outcome occur. So the very first one that we could see occur is that someone is sick for 0 weeks times the probability they get sick 0 of the 4 weeks was 0.45. Add to that the second outcome, which was being sick for 1 of those weeks, times the probability we're sick for 1 of those weeks, plus the probability, or plus the next outcome of 2 weeks times the probability we see 2 weeks, plus the next outcome of 3 times the probability we see someone sick for 3 weeks. And then the last outcome of 4, multiply the probability we see someone sick for all 4 weeks. Okay? Now, typically, when we're using these weights, we would then divide by the sum of our weights. But, right, if we looked at that formula sheet, and move this thing out of the way a little bit, my weights are probabilities. So if I add up the probability of every possible outcome, some of those weights or those probabilities should add up to 1. All right, so we essentially can ignore that. That's why there isn't a denominator here. Why complicate it? All right. So we can go ahead, add these up, and I think we get 1.05. Okay. But if we think about these possible answers, right, I probably could have ruled 2 of them out pretty safely, right? So if I look at D here, why could I maybe rule out that the mean was 2? If the mean was 2, what should be true about the values below that mean of 2 and the kind of values above that mean of 2? Yeah, they should be about equally as likely, right? It could be that, you know, they don't have to be the exact same probabilities, but they have to be close to each other, right? Well, if we look here, 0 and 1 are way more likely than seeing 3 and 4. So automatically we know we're not going to be smack dab in the middle of these values, right? We're going to be like a little bit closer to 0, right? It's going to be dragged down. Now, how much? That's hard to say, you know, without having like a really gifted mind be able to visualize these probabilities. But you know, 2 we can kind of rule out because the values below that are much more likely than the values above it. Now, 0.2 is probably safe to rule out. Why? I mean, it's so close to 0 that it would have to be that the outcome of 0 would be much more likely than probably 0.4. If we had, you know, probably of 0.8 or 0.9, that would pull that mean really, really close to 0, and then we might see a mean of 0.2. But right, given that we have the probability of seeing 1 and 2, like these are not, you know, very, very close to 0, it's very unlikely that the mean is going to be 0.2 or that low. So if I'm throwing darts at this one, I'm probably going to throw a dart at B or C, right? I'm going to try to hit B or C. one of those is more, a likely answer. Sure enough, if we actually compute it, right, it is 1.05. But I'm just trying to talk through the principles for helping us at least, if we got stuck on this one, I don't know what equation to use. If I just think about what I'm doing, I'm calculating the middle point of these outcomes, but I know that some of them are going to influence that middle point more than others, right? Just thinking through those principles, we could have ruled this down to probably, guessing between 2 instead of 4 options. So I know students don't like multiple choice sometimes, and they think it's, I don't know, hurts their grade more. I've tried writing questions with several more short answer or several more multiple choice, and I get about the same average either way. Sometimes, though, with these multiple choice problems, it helps. It helps improve grades if you aren't really sure where to begin, but you have or what formulas to use, but you have a really good understanding of the principles, right? Now, in a short answer, it doesn't matter how good your understanding of your principles are. If you don't know what function or equation you use, you're not going to get any points there, right? So I think kind of thinking through what answers you can rule out is a really good way to kind of work through some of these multiple choice questions. Okay. Any questions on that one before we keep moving? I don't think there's anything in the chat. All right, so this one's are a little bit unique, and if you're looking at other problems in the practice exam, you might see this as well. So anytime I write a problem where it's kind of related to the previous problem, well, I don't want to have cascading errors, right? If I asked you here to find me the standard deviation or the variance for this number of sick weeks, well, if you got the mean wrong, you're sure as hell going to get the variance wrong, right? You need the mean to calculate the variance. So if you get 14 wrong, there's no way you can get 15 right unless you guess, right? So I don't want that to be the case. So what I do is I give everybody kind of the same starting point. Assume that the average or the mean number of sick weeks you found was 2, right? So we're all starting out with a mean of 2. That's not the correct mean, but I'm giving you this assumed value to use, okay? So we have this mean of 2, right? And we want to calculate the standard deviation, right? Which is just a scaled version of the variance, which tells us something about how much do these outcomes vary from this middle point, right? Well, if I look at these possible answers, which ones can I rule out right away? Yeah, negative, right? We know variances and standard deviations have to be positive, right? Because it doesn't matter if we're varying from that mean above it or varying below it, that still counts as variation, right? There's no negative values there. So if we go to our formula sheet, how can we actually compute this? We can rule out one of the answers, but we still got 3 we got to choose between. Well, here's my discrete random variable equations. Here's the variance, right? Now, I don't have the standard deviation here, but once I find the variance, what's the only other step I need to use to find the standard deviation? Not square it, right? If I'm going from the variance to the standard deviation, I'm going to take the square root, yep. So I always kind of did this last class as well. So, right, we always have to calculate the variance first, and then to get the standard deviation, what we're going to do, that's just sigma, so we would have to take the square root of our variance. So we're going to first find our variance. We're going to go through every outcome, subtract that mean of 2 that we were given, square that deviation, and then multiply by the probability we saw that outcome for x. So if we go back here, what does that look like for us? All right. So how do I calculate this variance? I'm going to take that first outcome of 0, subtract that mean I was given of 2, right? We were assumed that mean was 2. Square that deviation, and then multiply it by the probability I see 0 occur, which was 0.45. Then add to that the next outcome of 1, subtract that mean of 2, square it, multiply that by the probability we see 1 occur, which was 0.25. Won't talk through the rest of these, otherwise I'll probably take a little bit more time than I want. But we just go through every possible outcome, subtract that mean, square the value, and then multiply it by the probability that we saw that value occur. So I'm just going to get this all written out for us. So if you're following along, you kind of have the complete thing. Right? Now, you could put this all into your calculator at one time. Another way to do this, and obviously you're not going to have the ability to insert a column next to it on the exam, but what you could do is on a sheet of paper in front of you, write your own column, where you have the different numbers of weeks, and you say, okay, for the first one, it's going to be 0 minus 2, so that's 2, squared is 4, times 0.45, so I get what, 0.9, is that, no, 85? 1.85? Yeah, okay. No, it should be 0.85, right? Am I thinking about this right? No, it is 1.85. 0.45 times 4. There we go, 1.8, my bad. I see what you're saying. Okay. Next one, 1 minus 2, negative 1 squared is 1, times 0.25, 0.25, right? And I could go through and do this for every outcome and then add them all up, right? So that's a way to kind of prevent from making maybe parentheses errors in your calculator or something like that, okay? Any questions on that one? So if we get this all into our calculator correctly, we should get 2.35. So we circle A and we're done, right? What did I just calculate? Calculated the variance. What did the problem want? Standard deviation. So the only other thing I have to do here is take the square root. That would give me my standard deviation. That's the 1.53-ish, okay, for rounding the second decimal. So this is an example where I might give you an assumed value, and then you use that, okay, so that you don't have kind of cascading errors here. Okay. Any questions on that one? Okay. All right, so one more problem in this kind of batch. So let's say I wanted to know what's the probability that you're sick for less than 2 weeks in February. Okay. So i.e., what's the probability that X is less than 2? So how am I going to find that? Right? Well, we did a lot of this with binomial and Poisson. It didn't really work through as many with, I don't even know if I completely worked through one with these discrete random variables, but binomial and Poisson variables are discrete random variables, are just very unique types, right? So if I want the probability that X is less than 2, and I think about this as event A, well, I can never see, these are mutually exclusive events. I can't see somebody be sick for 0 weeks and sick for 3 of the weeks, right? So this is, so when I think about the probability that X is less than 2, what I'm going to do is think about all the possible outcomes that meet this criteria, and add the probability up of each one of those outcomes. So what's the very first outcome or number of sick weeks that would meet the criteria of being less than 2? Well, 0 is one of them. What was the very first outcome that would meet this criteria? Yeah, X is equal to 1, right? Yes, it doesn't. When I say first, I'm thinking about the next lowest, but yeah, right? We've only got 2 outcomes that meet this criteria because I don't have a less than sign here, right? It has to be less than 2. Well, it's discrete. So the very first value that's less than 2 is actually 1, right? And now it's really easy. Unlike our binomial and Poisson, we don't have to use a probability mass function. I just use this table, right? Here is my probability mass function. So the probability X is equal to 0 is 0.45. Probability that it's equal to 1 is 0.25, right? And so I get what? 0.7 here. We're done, right? Easy as that. Now, this is where we have to be careful, like of the equalities. So if I had instead, what's the probability X is less than or equal to 2? Well, now the first outcome that really meets this criteria would be X can now be 2. So then I have to add in the additional 0.15, right? And I get 0.85. So we got to be careful with that equality there. Okay. What if I instead wanted the probability that X was greater than or equal to 3? What outcomes fit this criteria? X could be, yep. So X could be 3 or X could be 4, right? So we'll add those probabilities together. Once again, just a matter of going and grabbing those from the table. 0.1 is 0.05. You get that 0.5. Okay. Any questions on that one? That one shouldn't be too bad. As long as we be careful about the equalities, that one should be relatively easy. I say relative. So the next batch of questions we have, and we went a little bit quicker, but I do want to return to that one. So I'll start with this binomial. I'll kind of show you a couple things to kind of think about. And then I might return to that one about independence to show you an additional check that could be used like on a short answer that wasn't, you know, the one that we worked through. So let's say I've got approximately 64% of people in the US have a visual impairment, right? So they need, I don't know, glasses or surgery or something. Suppose we select 15 people at random, right? What's the expected number of people who have a visual impairment? Yeah, so why did you know right away? I mean, I don't know, maybe you did the math in your head of a formula, but actually there's a way where even looking at these, first of all, which of these can I rule out right away? I mean, very quickly. What would the percent have to be for it to be 15 out of 15 people? 100%, right? That doesn't make any sense, right? So really this is one of those intuitive ones where we said, well, if I had 100 people, how many people would need, you know, or have a visual impairment? 64. What'd you do in your head there? You actually were, you know, technically using this equation, which was taking the number of trials n times the probability of success in any one trial p. So here, this batch of equations is our binomial distribution equations. Here's our probability mass function. Here's our mean. Here's our variance. Here's our standard deviation. So to get the mean, it's simply n times p. So here for us, that was what? N was 15. Probability of success is 0.64. If I multiply this, it was 9.6. Right? So I could have also asked you what's the mean and what's the variance. There is just a matter of here. We've got our binomial distribution equations. I just plug in my n and p into this equation to get my variance. Okay? Didn't ask you that in this problem, but it could ask you that on a problem like this. Now, another thing to just kind of point out so we start to think about some of these principles. Even if I couldn't do this math in my head, why do you know it's not B and C? Here's a trick to kind of put a bounds on it, right? So 64% is more than half of the people, right? So let's use the 100 people example because it's easier. If I have 100 people, I know that 50% of 100 is 50 people. I have that 64% of people will have a visual impairment, so I know that it's going to be greater than 50, right? Same thing here. If I have 15 people, I know that more than half of them have a visual impairment. What would half of 15 be? 7.5. So I know that more than 7.5 people are expected to have a visual impairment. Only one of these values is greater than 7.5. Right? So even if I don't know, if I didn't have a calculator and I want to do this, couldn't do this in my head, 0.64 times 15, just looking at these options, I know that it has to be A. Well, I mean, I guess D is greater than 7.5, but it's also less than 100, right? We could put upper and lower bounds on where this probability has to be, or where this expected number of people has to be. I mean, this one we'll talk through, and then I'll kind of return. This one shouldn't be too bad. If I have the same setup, but I want to know what's the probability 10 of the 15 have a visual impairment. I go to my formula sheet. If I want the probability of any one number of successes, the probability x is equal to, I think it was, what did I say now, 10 there. I have to use this equation, right? My number of trials was the 15 people, so that was n. Probability of success was 0.64. And now my x, the number of, the number I'm trying to find the probability of is 10, right? So it's a matter of plugging those values in and being able to work this out in our calculator. So this is where we said it's important to know where your factorial button is, right? Or if we write this out, being able to see like what could cancel here, okay? But really this is practice at, I can write this out for you, but I mean, really once we have n, x, and p, it's a matter of you being comfortable entering that formula into your calculator and being able to get the correct answer. Okay. If we look here though, I mean, which of these, if I think about the answer of D here, right? So on average, we said 9.6 people have a visual impairment out of 15. So 9 and 10 are going to be pretty likely outcomes, right? Let's just assume for a second they're the only two outcomes we could see. We know that's not true. We could actually see anything from 0 to 15. But even if they were the only two outcomes, And let's say they're approximately equally as likely. So if they're the only two outcomes and they're about equally as likely because they're both kind of on either side of the mean there, what would the probability of each one be? About 50%, right? 0.5. So if I'm thinking about the probability of 10, even if that was a scenario, I eliminated a ton of the other outcomes and I only had two that were, both equally as likely, D doesn't make any sense. For the probability to be as high as 0.9, right, that would mean that that's really the only outcome that we're typically seeing. Well, we know here that 9.6 is the average outcome we see, or that's our mean. So on most cases, we're going to see either 9 or we'll see 10. They'd probably be equally as likely. So if we're going to be equally as likely, you can't have a probability as high as 0.9. Anytime we find these probabilities for a binomial, you can almost cap it at 0.5. Like it's unlikely that something is ever going to have a probability of occurring of 0.5 or higher, right? Now, how much lower can you go? I don't know if B or C. I don't know which one makes any more sense there. It's now we can't really say anything about that. But anything over 0.5 doesn't really make a whole lot of sense in the context of this example. And I also, in explaining that, eliminated all the other outcomes that we will see, which are 0 through 8 and then 11 through 15, right? So we know the probability can't be too high here because we have so many outcomes that we could see, and 9 is going to be just about as equally as likely as 10, and really 11 and 7 aren't that far away from the mean. They won't be that unlikely. So for us to get a probability of any one outcome of being as high as almost 0.7 or 0.9 doesn't really make a whole lot of sense for what we're doing in this example. If I'm just taking a shot in the dark here, just off the principles, and maybe I can't put that formula into my calculator, I'm going to guess B or C here. And I don't, if we work it out, wouldn't be something if I explained all this and then it ends up being 0.9. No. No, these principles we can see, yeah, so it ends up being 0.2. Right? There's no way we could see it be as high as kind of that 0.7 or 0.9. This doesn't make sense for what we're doing with a binomial with this probability. Now, if I instead said like, well, let's assume that the probability someone has a visual impairment is 0.0001. Well, yeah, then maybe the probability we see 0 is that high, but for the sake of the numbers we have here, it doesn't make a lot of sense.